So, one of the beautiful things about molecular orbital theory, other than its very clear connection to the quantum model of the atom, is that it helps explain resonance structures in a much more straightforward way. And now we're not going to go into a lot of depth here, strictly because we've really only looked at what happens when we make MO diagrams for just bringing two atoms together into a covalent bond. Getting larger than that makes it a little bit more difficult to map out on paper and gets closer to being in the realm of things that we would need to do computationally. And so we're gonna be a little brief here, I will admit. But the thing is when we're looking at even those diatomic molecules that just have two atoms, what we're doing is we're taking all of those atomic orbitals and we're combining them into a set of molecular orbitals that apply over the entire molecule. And when we do that, when we create a set of molecular orbitals for the molecule rather than focusing on what's happening at each individual atom in the molecule, then it's easy to see how electrons can be delocalized over the entire molecule. And that's really the foundation of what a resonance is, or resonance structures are, is that it's trying to represent delocalization of electrons across multiple bonds in the molecule itself, something that Lewis structures can't really describe without drawing lots of them, right? And even valence bond theory doesn't really explain it well either because it's all focused on the atom. So when we get bigger than two atom molecules, we're still doing the same thing. We're still taking all the atomic orbitals from all of the atoms, combining them into a set of molecular orbitals that represent the entire molecule. And then we are saying these valence electrons belong to the molecule and not to this specific atom now that we're bonding. Now, if that atom's completely alone, they're just atomic orbitals on the atom. But once it starts participating in a covalent bond, then it becomes the molecule's valence electrons and they can be distributed over the entire molecule and it's much more flexible. Then that molecule can kind of redistribute electrons in a reaction to what's happening externally. And so when we think about a resonance structure, and we talked a lot about this in our previous chapter with ozone right here. Here we go. So here's our Lewis structures that are trying to show resonance by having two equivalent but different Lewis structures. And for valence bond modeling of covalent bonds, we would still be kind of trapped in that same thing where we can create one that represents kind of one picture of this molecule, but then we would have to draw another one that showed the double bond in between the other two oxygens. But when we take all of those atomic orbitals and we pull them away from just the atom and make them part of the whole molecule, we make them a community of orbitals, whatever, then what we get is a model for resonance that says, well, because these are molecular orbitals, those electrons can be distributed across the entire molecule and are. And so then you get these, without having to draw multiple structures, you get this one clear picture of, well, yeah, the bonding order at this at each of these oxygen oxygen bonds within this molecule are 1.5. And that's just without having to think of it as being two bonds and one bond that can kind of flip around and move things around and be two and one here. Instead, we just build something that just has a bond order of 1.5, and it doesn't have to be estimated. And so that's kind of the power behind this model in part. Not only does it help us better predict like whether or not a molecule will be diatomic or paramagnetic, um, it also predicts bond orders accurately. Bond lengths and bond strengths is what that means. And so it gives us a much clearer picture. And so while you will not be expected to build a molecular orbital diagram or picture for a molecule that has more than two atoms, it's important to look kind of beyond the simple version that we're working through and see the implications for larger molecules that do have resonance structures or do have delocalized electrons that play a really big part in its reactivity.